All right, guys, welcome to Precalculus 114. This is going to be a lesson that's maybe going to feel a little bit more like a physics lesson. We're going to be doing a lot of kind of analysis and kind of rates of change and how those things relate and how we can affect those and change those. So what I want you guys to do first is to go ahead and check your pulse. To make it really easy one is here on your jugular. Go ahead and do that for 15 seconds. Count the number of beats you count in those 15 seconds, and then go ahead and resume the video. So go ahead and pause and do that now. All right, now that you have your number of beats in 15 seconds, we want to convert that into how many beats per minute you had. So figure out, hey, how would I do that if I do my beats per 15 seconds? What is going to be your beats per minute? Easy way is going to be multiplying that by 4 because there's 4 15-second periods in a minute. So we're just trying to kind of convert units here. This is kind of that basic skill there. So then let's talk about a few things. So first of all, what do you know about heart rates? Right? How can I increase my heart rate? Are there ways that I can decrease my heart rate? And then how could you determine your number of beats per hour? Right? So we're just trying to find all of these kind of averages now. Hopefully that's not too challenging, and we're going to go ahead and move on to the next lesson here. All right, so number 29. So this is actually a story about how some toll booths work, and it's a very ingenious, but on my end, it's also very just like feels kind of scummy of a way to do things. So toll booths, you'll see them in bigger cities, especially around bridges. But they're a lot more common back east than they are here in the west. But basically, for some interstates or highways, you have to pay a toll to get on it, or you don't pay a toll to get on. You get on, and then you drive ways, and then you get off, and you pay a toll there, right? So what they do is once you get on, the little ticket they give you says the exact time you were at whatever booth you got on at. When you drive and then you get off at the on-ramp you want to get off at, right? And then you give them the ticket there and you pay for using the road. And what they will occasionally do is say, hey, based off of the time you left, you were actually speeding to get here, so actually here's your speeding ticket too, right? Which really, you were speeding, but like it really feels kind of weird. But so the question kind of becomes, well, how could they determine that you were actually speeding by doing that? Well, they could fairly easily take and this is what they actually do, is they take your distance traveled and the time it took you to get from where you got on to where you got off, and then they average that and say, well, if your average speed is at or above the actual speed limit, we have evidence that you were actually speeding. And so here is your ticket. And it makes sense, but it also feels just not very good, right? So let's talk about kind of how that like works, right? So if you, let's say it's 60 miles and it took you 1 hour, just make it easy, it's 60 miles per hour, and you get there exactly 1 hour after you got on, and you might say, hey, it took me 60 miles to travel it took me 1 hour to travel 60 miles, so I clearly was going at the speed limit of 60 miles per hour. I don't get a ticket, right? But that's actually false. They can use that as evidence to prove, yes, you actually were speeding. So how that works is, when you started off, you were at a speed of 0 and you had to accelerate up, right? And then when you slowed down to actually pay your toll, you slowed down and went from wherever you were down to 0. So for those instances of like time, your speed was actually less than 60. So for your average to be 60, there had to have been some point in time where you were going over 60 miles per hour. So since they can guarantee and prove, yes, there was a time you were going under 60, there has to be a time that you're going over 60 for your average to be 60. So that's how they can actually kind of do that kind of stuff. So we're going to use that here in problem 30. So in 30, we're going to be traveling a distance of 28 miles in 30 minutes, right? So that's our time spent on the freeway. So what was our average speed in miles per hour? So if we traveled 28 miles in half an hour, what's our miles per hour? What's going to be kind of double that? Right, so we're going to be at 56 miles per hour, right? As our kind of average speed there. So what we want to do is kind of, let's sketch a graph of what this would actually look like, right? So we actually had to start at 0 speed, and then we had to accelerate up, and then do we accelerate up to 56 miles an hour, and then just go there, and then go back down to 0 once we get to our destination? No, right? We have to at some point go above that 56 miles an hour, and then go there for a while, and then we could go up and down a bit, and then we could go back down, so that our overall average would be that 56 miles per hour, right? So then we get down to question C, right? Or sorry, B. Sketch a possible, sorry, we said that. C. Did Marcos drive his average speed the entire trip? Well, no, right? For you to do that, you would go instantaneously from 0 to 56 miles an hour, which would kill you instantly if it was instantaneous, right? You have to have that acceleration so that your body can actually adjust to the actual speed, right? So you went from 0 and then accelerated up to at least 56, but could you just go there and then stop, right? No, we had to go higher than 56 in order for the average to be that 56, like we mentioned earlier with that previous problem. So the question part D is, did he ever drive the average speed of 56? So if he wasn't there the entire trip, was he there at some point? And we can actually guarantee yes, he had to at some point, maybe not for very long, but as he was speeding up, at some point he had to cross that 56 mile per hour speed to get up to that like maybe 60 or 61 mile an hour he was cruising at or whatever, right? So that's how we can kind of, that's the main thing we're trying to kind of get across here, right? The average speed versus what it actually was, because in order to get that average, we have to have some of it be lower and some of it be higher, and that's going to be our main kind of goal today. Okay, so let's take a look at problem number 31. So here's our kind of next step here. We have a rainwater collection tank, and it can hold 1,000 gallons, right? And the water is filling up at a rate of 0.05 times T gallons per minute. Okay, so what's going to throw you off initially here is that rate, or that equation, is an equation for the rate. It is not a rate of 0.5, it is a rate of 0.5 T. So the rate is changing over time. Okay, that's also called acceleration or deceleration, right? So that's something that you want to keep in mind. So what I want you guys to do is go ahead and pause, try out number 31, and then also try out number 32. Once you've done that, go ahead and resume, and we'll kind of talk about what's going on at these points. Okay, so on part A, you should have a graph. Now, the graph of the situation, it depends on kind of how you label these. If you did a graph of time as your x, in gallons per minute as your y, this will be a linear graph. If you did a graph of time to gallons, it's not going to be that. It's going to be increasing in its speed, right? You're going to see that kind of curve like an exponential graph there, because we're actually increasing our rate as time goes on. We are accelerating. So this is really trying to get you used to the idea of a position graph versus, or a amount in this case, versus a velocity graph or a rate graph, right? It's really easy to graph distance to time, but if you're trying to graph, if you have distance to the actual rate, that's going to give you much more complex graphs here. So, how fast is the tank filling up at 10 minutes? Well, I can find that by doing 10 times 0.5, so I'm going to be having 5 gallons per minute at 10 minutes. At 20 minutes, I plug in 20 times 0.5 is 10. So at 20 minutes, I am getting 10 gallons per minute, right? And then at 30 minutes, I'm getting 15 gallons per minute, right? So what does that tell you about how fast the tank is filling up? It's filling up faster and faster as time goes on, right? So that leads us to the rest of the problem here, which is how could we describe the rate of 0.5 T gallons per minute and as it relates to how fast the tank fills up, okay? So we know that it's going to be increasing in its rate as time goes on. So we actually see a graph that may look kind of exponential in a way. Let me actually grab my paper. Okay, we'll sketch this out quick. Sorry, I didn't have this out yet. All right. Okay, so here's paper. So we're going to see that if I have my graph, and this is my time, and then over here, this is my gallons and tank. Okay. It's going to start at 0, but it's not going to be constantly filling up at a constant rate. That would be a linear graph. It's going to be increasing as we go, so it's actually going to have that kind of exponential curve, where I'm actually increasing by 0.5 gallons per minute every minute. Right, so I should see that kind of slow, gradual increase, that kind of exponential curve. Again, this isn't a perfect graph, but this should be kind of what we are seeing here. So if I want to figure out, well, how many gallons do I have? Well, this is the kind of tricky part, and I really just want you to kind of think about it. We are going to go over the actual process in the future, but how could we, from that graph, figure out how, at what time we overflow, right? When are we going to have too much? Because at 1 minute, I'm gaining half a gallon per minute. So then does that mean, hey, that's half a gallon, right, over that time? Because but then if I go a little bit under 1 minute, I'm filling up slower, but if I go a little bit over a minute, then I'm going faster. But how does that relate to the average? So again, I'm purposefully not giving you the answer right now because I want you to kind of think about it and how could you find this out, right? And then based off of your predictions, try and answer part D, right? If his predicted rate is correct, will the rainwater tank overflow in less than 1 hour? And try and support that in whatever way you can. Again, I'm purposefully withholding the answer because this is about exploring and thinking about it more than it's about, hey, here's what the answer is. All right, and number 32. The child tosses a tennis ball into the air and it lands in the mud. The function negative 16 t to the second plus 16t plus 4 gives the ball the ball's height in feet with respect to time in seconds. So this is time and then a distance measurement, a height measurement, right? Which is our last one. We were kind of given time and then a rate. So on this one, if I sketch a graph of this, what should this look like? Well, you can kind of already make a prediction, but if we pull up Desmos, we can actually graph this relatively easily. So let me just change this over to a Desmos view for you. And then, so we're going to be graphing, it is negative 16. I'm going to use x as opposed to t because Desmos prefers x's. Minus, is that minus or is it plus? I can't see very well. It's plus, sorry. Okay, that should be a 16, not a 15. Plus 16x plus 4. So here is our graph, right? So the only parts that we really care about are from here up to there and then down and stopping at that point there. So that's the actual part that we care about for the graph, right? So back over to this. What is happening to the height as a tennis ball with respect to time? So the height is going to increase for a little bit, and then it'll get to that peak, and then it'll start to decrease, and then it'll stop once it gets down to that ending point. So it'll rise, and then it'll kind of stop rising, and then it'll start to fall, and then it'll stop once it hits the mud there at the x-axis. Right, and then part C here, since velocity is a function of distance traveled over time, what part of the graph represents the velocity of the ball? So this is one of the kind of big questions, and if you've done a lot of physics, this should be kind of second nature to you. But if you haven't, that's where I'm kind of going to assume you kind of are. So my velocity is my average rate over time, or my distance over time is velocity, right? So if I were to say, well, from here at time 0 to here at time 0.5, I went from 4 to 8. So that is me going 4 feet, or 4 inches, or whatever. So 4 feet over a time of half of 1 second. So that would be 8 feet per second would be the average rate from here to the peak. Now, does that mean that it's traveling at 8 feet per second the entire time? No, right? At the start, it's really not really traveling much at all, and then here it's traveling 0, but the average over that time is going to be that 8 feet per second. So there's some time when it's going faster, some time when it's going slower, but average-wise, that's how I would do that. It's about finding a start point and an end point, and you're finding the average over those two times. All right, so back over to this. Since the velocity is a function of this, sorry, I just did that one. What is happening to the velocity of the tennis ball with respect to time? It's going to be decreasing as we go up towards that peak, but once we're at the peak, it'll start to actually increase again, but just now in a negative direction as it goes down towards the mode, where it just then instantaneously or almost instantaneously stops. Right? So then we can actually take this table and then fill out the different values based off of the equation. So we can plug in 0, plug in 0.25, plug in 0.5, 0.75, 1, 1.25, 1.5. So go ahead and do that. And then what I want you to do is, like I just did here, find the average feet per second, the rate of change between all of these intervals. So find the average change here, 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 and the average change here. So go ahead and do that. Pause and then come back and we'll finish this off. Okay, so at this point, we should see a change in that average speed, right? We should be going pretty fast, and then we're going to be slowing down as we're kind of approaching that 0.5 time when we're actually going to be peaking, and it's actually going to be kind of transitioning from being a positive increase to now a negative as we're now going downwards. And then it starts to get faster down and faster down as we kind of go down in that direction. So what we're really trying to focus on right now is finding the average rate of change between those different intervals. And we can make those intervals smaller and smaller and smaller and find more and more precise rates of change as we kind of go there. So with that, I want you guys to make a prediction as to what would the velocity of the ball at time 0.8 seconds be. So that's probably going to be somewhere between here and here, right? Is it going to be exactly the average, or is it going to be a little nearer to what the average is on this one? Make a prediction, justify it to yourself why you are making that prediction. All right, and then with that, hop back over here. We're going to call it a closure here. Now, for our closure, I gave you this really weird graph that I made purposefully weird because I want you to focus on the wording as opposed to just using your intuition of what speed and acceleration and all of that kind of things are. So I have a graph here of toothpicks to wrenches, or wrenches to toothpicks, depending on how you want to say it, right? So how is the number of toothpicks per wrench, so that's a rate, so the rate of toothpicks per wrench changing as the number of wrenches increases? And how do you know that? So think about that for a second. How is the toothpicks per wrench value changing as wrenches are increasing? pause, think about that, answer the question, and then go ahead and resume here. So my rate of toothpicks per wrench is actually increasing. This is much like the one we saw there here with the rainwater, right? I'm going upward very slowly here, but as I go further right, I'm going upward faster and faster and faster. So I'm going more and more steep. So as my steepness is increasing, my number of toothpicks per wrench is increasing as well. So we're trying to say, hey, what's the correlation here between that rate of toothpicks per wrench? How does that relate to the actual situation? So toothpicks per wrench is a rate of change. And we have another kind of math term for rates of like change and how those look in like graphs. That's my little hint for you of how the rate of change is visible in this type of graph. So we'll cover that more in the future, but I wanted to kind of leave you with that little teaser to make you kind of wonder and think about how these things are all related. So with that, here is our homework 33 through 39. Go ahead and give that a go, and I will talk to you guys next time.